Principal component analysis. Before moving to the coding session, I will first explain principal component analysis theoretically. Principal component analysis, namely PCA, is a broad and important topic in machine learning, data science, and statistics. Many widely used programming languages provide built-in functions for PCA computation, making it easier to apply to a dataset and obtain results. However, as machine learning practitioners, we must develop a deep understanding of PCA, its mathematical foundations, and the key terms associated with it. This knowledge enables us to implement PCA effectively in our projects. By applying PCA, we can gain new insights into our dataset, which can lead to improved model training and better prediction accuracy. Therefore, in this lecture, I will take sufficient time to explain PCA, including its mathematical foundations. Finally, we will go through two practical examples to demonstrate how to compute PCA. Namely, principal component analysis, PCA, is often used as a method of data compression. It allows redundant data to be compacted into fewer components, meaning the dimensionality of the data is reduced. The components of the PCA are uncorrelated and independent, and they are often more interpretable than the original data. PCA is a dimensional reduction technique commonly used in machine learning, data analysis, and statistics. It transforms high-dimensional data into a smaller number of dimensions, namely principal components, while preserving as much information as possible. PCA is particularly useful for visualizing data, reducing noise, and simplifying models. Now, let's see the key concepts of PCA. First, dimensional reduction. PCA reduces the number of features, namely dimensions, in a dataset while retaining the most important information. Second, variance maximization. It identifies directions, namely principal components, in which the variance of the data is maximized. 3. Orthogonality. The principal components are orthogonal, namely uncorrelated, ensuring that the information captured by one component doesn't overlap with another. 4. Linear transformation. PCA is a linear technique. It assumes the data can be represented effectively in a linear subspace. Namely, PCA has this much key concepts. In the following section, we are going to discuss each item one by one. Now, let's see how PCA works, namely, what kind of steps we have in order to perform PCA for a dataset. First step, standardize the data. Center and scale the data so that features have a mean of 0 and a standard deviation of 1. This step ensures that no features dominates due to its scale. If features have different units, for example meters or kilometers or centimeters, standardization ensures that all features contribute equally to the principal components. PCA is sensitive to the magnitude of features because it relies on variance, which is scale dependent. However, if features are in the same units and have similar ranges, PCA can perform effectively without standardization. In the following section, we are going to see two examples. One for the scaled data, namely, we will scale the data prior to the PCA. One for without standardization, namely, we are going to see two examples. Step 2, compute the covariance matrix, namely, calculate the covariance matrix of the standardized data to understand the relationship between the features. Step 3, calculate the eigenvalues and the eigenvectors. Compute the eigenvalues and the eigenvectors of the covariance matrix. Actually, eigenvalues explain the variances and the eigenvectors explain the direction of the principal components. Later we will see this. In the step 4, we will sort and select the principal components, namely rank the eigenvalues in descending order and select the corresponding eigenvectors to form the principal components. The number of components is typically chosen based on the proportion of variance to retain. Namely, in the most of the cases, we are going to retain 95% or 97%, that kind of information. Therefore, PCA is a dimensional reduction. Namely, we are going to remove some kind of less significant information and keep or retain most significant information. Step 5, transform the data. Project the original data onto the selected principal components, producing a new dataset with reduced dimensions. These are the 5 steps of the PCA. In the following section, we are going to see these 5 steps. First, in mathematically, we are going to talk about the mathematical foundation of the PCA, namely mathematical correspondence of these 5 steps. Then we are going to see 2 examples. What is PCA mathematically? Let's assume that we are given 2 variables x1 and x2 and aim to understand the underlying theory behind the PCA using this simple 2 variable cases. The following are the principal component analysis steps for this scenario. Namely, this scenario, we are given 2 variables x1 and x2. In this simple cases, we are going to learn what is PCA mathematically. In the first step, mean centering. Namely, we have the original data. Now, first we calculate the mean for each feature. Then we do the subject. Namely, after we calculate the mean for each feature, for example here, mu1 is the mean of the first feature, mu2 mean of the second feature. Therefore, by using this operation, namely subtract the mean of each variable from its respective values, we are going to calculate the mean centering process. Namely, this step centers the data so that each variable has a mean of 0. After this step or after this operation, we get 2 new features. They have a mean of 0. This is the first step. In the second step, we need to calculate the covariance matrix. Namely, calculate the covariance matrix using the mean-centered data from the first step. In the first step, we know that we have calculated the mean-centered data features. Therefore, by using that feature, we need to calculate the covariance matrix. The covariance matrix serves as the foundation of PCA. The covariance matrix is structured as this is the covariance matrix, where x1i and x2i represent individual data points in the features. mu1 and mu2 represent the mean of x1 and x2 respectively, and represent the number of data points or sample points. Then sigma square represent the variance. Now let's see this. In the first step, in the numerator, we have a multiplication, then we have the summation. Namely, first we are calculating the subtraction. Namely, we calculate the mean, then we calculate the mean for the second feature. After that, we just find the subtraction, and then this is the same. The corresponding element is multiplied, then sum it around the sum it from 1 to n. Okay, this gives us numbers. Then here in the denominator, we have n minus 1. Actually, we are calculating the covariance matrix for the sample data, not for the entire population. If we calculate it for the entire population, at that time we need to use only n. But in the real world scenario, we always calculate the covariance matrix for the sample, namely limited number of sample points. Okay, then after that, this formula can be represented just like this. This is a symmetric matrix. In the diagonal elements, we have variance of the first feature. We have variance of the second feature. In the off-diagonal elements, we have covariance between the x1 and x2. We have covariance here between the x2 and x1. In other words, we can represent this as just like this. Namely, these diagonal elements are the variances of the first feature and the second feature of diagonal elements are the covariances of the x1 and the x2 or x2 and the x1. Therefore, covariance matrix is a symmetric matrix. Actually, this variance can be calculated just like this for the entire population. In the case of here, we are using two features here, namely x1 and x2. If we only have one variable here, we can calculate or we can assume the variance just like this. Here we have multiplication, but if we have only one variable, it's very easy to see that this should be became to square. That's it. That's the variance, and this is the variance, this is the covariance. Namely, variance is represented along the diagonal elements, variability of x1 and the x2. Then covariance is represented in the off-diagonal elements. They are shared variability between the x1 and x2. Covariance x1 and x2 equal to covariance x2 and x1. Actually, this is same thing, namely just the order. Therefore, off-diagonal elements are the same. Please note that this is a simplified case. We have only here two variables. In the case of 3 or 4 variables, we will get more complex matrices. However, in any case, we will get symmetric covariance matrices. Then, covariance measures the direction of the linear relationship between the two variables. Positive covariance, variables increase together. Namely, they have a kind of correlation, namely positive correlation relationship. Then, if these values are negative covariance, at a time one variable increases as the other decreases. Namely, it's just like the negative correlation. Then, if we have zero covariance, namely zero covariance, at a time there is no linear relationship between x1 and x2. These are the value range, these are the meaning of the covariance values. Okay, let's see a simple, very simple example. Let's say we have a list with 5 elements. The minimum value is 48, maximum value is 51. Then we have second list here. Minimum value is 10 and the maximum value is 90. In these cases, in both cases, the mean are the same, namely 50, 50. However, in terms of variances, the first list has small variance, the second list has large variance. This is very interesting. Let's see here. The fluctuation of the values are small. In the first case, the fluctuation of the items in this list are big. Namely, we have the minimum value of 10, we have 30, 70, 50. Therefore, items, namely the fluctuations between each item or respective values are big. Therefore, we call it large variances. In this case, only difference, namely range is from 48 to 51. We call it small variances. In this example, the values fluctuate more, resulting in higher variances. In this case, the values fluctuate more. Therefore, this list resulting in higher variance. In the step 3, we need to calculate eigenvalues and eigenvectors. In the previous step, we just calculate the covariance matrices. Now, we have covariance matrices in our hand. Therefore, we need to decompose the covariance matrices into eigenvalues and eigenvectors by solving the equation, just this equation, because this is the covariance matrices. In terms of linear algebra, we can decompose it to eigenvectors and the eigenvalues. Namely, this is the eigenvalue and this is the eigenvectors. Eigenvalues, lambda 1, lambda 2, because we have here only two variables, therefore we need to have two eigenvalues here. the eigenvalue represents the amount of variances explained by each principal component. Actually, this is the amount of the each principal component. Later we will see it. Then eigenvectors. Actually, eigenvector represent the direction of the principal component. We just mentioned that we are going to find the variance, namely which direction the variance is big and where the variance is large. The eigenvalues represent the amount of variances, then eigenvectors represent the direction of the variances. This is the one of the most important concepts in the PCA. In the following section, we are going to see the relationship between the eigenvector and the values of the covariance matrices. Now, let's see it. First, we just calculated this covariance matrices and then we decompose it into eigenvalues and the eigenvectors. Now, we have here eigenvector, eigenvalue, and we have here variances and then these covariances. Actually, there are several elements. We have here 4, then we have here 2, and then we also here 2 eigenvalues here. Now we have 8 elements here. Actually, these 8 elements are correlated each other very closely. Now, in this figure, we are going to see it. The direction of the eigenvector 1 will define it by this, namely the first variance and the first covariance. Namely, eigenvector 1 defined by using the first row, namely variance of the first x feature, then covariance between the x1 and x2. Then the second vector is defined by using the second row, namely this is the x1 component, namely in the x1, then its x2 component is the covariance of the x2. Namely, this row representing the first eigenvector, second row representing the second eigenvector. This is the endpoint of the first eigenvector. This is the endpoint of the second eigenvector. Later we will see this is very important, namely this endpoint of the eigenvectors are very important because we use it soon. Therefore, variances and the covariances of x1 and x2 along with the eigenvector direction. Therefore, this is the relationship between these 4 elements and between the eigenvalues and the eigenvector. I repeat again, the first eigenvalue defined by the variance of the x1 and the covariance of the x1 and 2, and the second eigenvector defined by the covariance of the x2 with x1 and the variance of the x2. Now we know that we have here endpoints of the eigenvector 1, eigenvector 2. If we draw a line through the ends of the eigenvectors 1 and 2, we can form an ellipse, namely this dotted line when the dataset consists of 2 features. Namely, this ellipse is passing through the first endpoint, passing through the second endpoint. At that time, we just form this ellipse. Okay, now the major and the minor axes of this ellipse correspond to the first and second principal components respectively. We just form this ellipse. The first axis, namely the major axis of this ellipse corresponding to the first component, namely first principal component, then its minor axis corresponding to the second principal component. This is very important. When there are more than 2 features, now we have only feature x1 and x2. If we have more than 2 features, an ellipsoid is formed and its axes correspond to the principal components of the dataset. The axis represents the direction of the maximum variance, namely in this case the maximum variance is this direction. The principal components are orthogonal, namely this is the first principal component and for example this is the second principal component. They are orthogonal, namely they are uncorrelated. In other words, for example, we have see here actually this is the x1 and this is the x2. Now let's see here a kind of rotation. Namely, actually, we rotated it. Namely, PCA rotates the axis to align with the direction of the maximum variance in the data. Actually, the variance is, namely, most of the variance lies in direction. Therefore, actually, this is equal to a kind of axis rotation. Therefore, until now, we have seen what is PCA mathematically. From this figure, and then from this ellipse and their relationship with the eigenvector 1 and the eigenvector 2, we just calculated, we just defined the major axis or minor axis of the ellipse, namely the major axis corresponding to the first principal component, minor axis corresponding to the second principal component. This is for two-dimensional, namely two variable simple case. In the real world scenario, we might have 3 variables, we might have 4 variables, we might have 10 variables. At that time, instead of ellipse, we need to draw ellipsoids. That ellipsoids, major axes or minor axes corresponding to the first, second, or third principal component. This is the meaning of the principal component in terms of mathematically. Therefore, now we have a pretty good understanding of the PCA in terms of mathematically. Finally, step 5, we need to transform the data. Actually, now we have the eigenvector 1, eigenvector 2. The issue is how we transform the data, namely how we do the PCA. This is the final step, because now we have the eigenvector. The first eigenvector, second eigenvector, namely we have the endpoints of the eigenvectors. Then we have the features, namely we have the feature 1, feature 2, namely this is represent the feature, this is represent the matrix of the eigenvectors, namely eigenvector 1, eigenvector 2, and then this is the transformed data. Namely, we just calculate the dot product of the feature between the eigenvectors. This operation will give us the transformed data. Namely, this is the result of the principal component analysis. Transform data to the principal component space. In this space, the data is aligned with the direction of maximum variances. For example, in this situation, the maximum variances is aligned with this direction. This is the second principal component. This is the second large or second largest variance direction and amount. And by using this product, we just calculate, we just transform the data. Namely, in this data, we have the first principal component and we have the second principal component for this case, for this scenario. This is the meaning of the principal component. We had 5 steps here. First, we calculate the mean centered data. Second, we calculate the covariance matrix. And the third step, covariance matrix decomposed into eigenvalues and eigenvectors. And step 4, we just define the ellipse. Then step 5, now we have eigenvectors, namely direction of the variances. Therefore, by using this vector, we just transform the data to the principal component. These 5 steps are the mathematical foundation of the principal component analysis. Now, in the following section, we are going to see 2 examples. Now, let's move to the coding section and see the examples one by one.